Okay, this lecture is going to continue with discussions of drag forces. The very first lecture, where we had begun discussions on the drag forces, we saw that drag forces are due to the viscosity of a fluid. However, they can be modeled two different ways. One as a bluff body with pressure drag, and the other as a streamlined body, and we called that friction drag. And we've looked at different ways to calculate that. Friction over a flat plate, some theoretical calculations using bluff bodies, from experiments, getting coefficients of drag, and we went over how to come up with the coefficients of drag if we were able to perform experiments on models, and discuss some general ideas of how to utilize that process that we had utilized for lift and scaled. So we didn't actually do those calculations or work, but that is a similar thing that we can do. So, focusing back on drag, we can get a coefficient of drag. And again, the coefficient of drag can be thought of as a pressure drag, a bluff body, where the area is perpendicular to the flow, or for friction drag, which is a streamlined body where the area is parallel to the flow. You can almost feel the difference in the different situations. So when you're standing up and on a very windy day and you're trying to walk towards the wind, you actually can feel the air hitting you. What you are effectively doing is you're stopping the air molecules. This important process is going to be momentum. You are basically taking the momentum out of the air. Mass times velocity is going to be momentum. The air is moving at a certain velocity, hitting you, and therefore providing, what you are doing is you're actually stopping the airflow. Air is going to have a certain amount of mass, and if it's moving at a velocity, you will have a certain amount of momentum. That's where you're going to be a bluff body in the area is parallel to the flow. If the air is blowing this way, this is my cross-section or profile area. Therefore, I will have a force due to that. You can feel or think of this as different. Now, think about when you're swimming. That is where you'll be a streamlined body. And you can almost feel the difference of the water. Now, again, it's not really, well, it would be sticking to you. It is sticking to you. Maybe it's different than if you were swimming in molasses. But if you're swimming in water and you're going to the flow, or if the water is flowing over you, you'll feel the water sticking. That will be a frictional flow. That can almost be compared to if you're in a physics class, if you have taken a physics class, where you have static friction. Friction on the surface, or the other case, conservation of momentum. So again, when you're performing these experiments or doing the calculations, you always have to be thinking of conservation of mass, momentum, and energy. All right. So just comparing and contrasting the different experiences that each of us have had. So the coefficient of drag can be split into two components. Coefficient of drag equals coefficient of drag due to pressure plus coefficient of drag due to friction. So let's use a useful application and do a calculation using both of these. That would be something that you could see in different situations. We're going to model a drag race car. That is going to stop utilizing a parachute. So when the car is going, it wants to have the smallest amount of friction possible so it can accelerate. But trying to stop, that's not going to be very, very helpful. So let's model the car as a flat plate. And the parachute as a bluff body. Where the coefficient of drag due to pressure for the bluff body is 1.2, and the diameter of the parachute is 1.5 meters. So the diameter of the parachute is going to be 1.5 meters. The parachute has a coefficient of drag of 1.2. We're going to model the car as a flat plate. So if we look at this, we can draw. Now again, I'm not an artist, but this could be our car. It's going to have a race car, so it's going to have a pretty small profile, but it's going to be long. And let's say the car is going to be modeled by 3 meters long by 1 meter wide. So it's going to be 3 meters and 1 meter in depth. And then we're going to model the parachute out here, which is going to roughly have a diameter of 1.5 meters in the coefficient. So we're going to have two different forces acting on it. Force of a flat plate, streamlined body, force of a bluff body in a flow. So let's look at if the car is traveling at a velocity of 5 meters per second. We have to do two separate calculations. We have to do the calculation on the car, the force of friction on the car, and then also the force of friction on the parachute. So if it's moving this direction at 5 meters per second, this also is moving 5 meters per second. Therefore you have a force of drag moving in this direction, and also a force of drag due to the bluff body. So the force of drag of the parachute, force of drag of the car. Force of drag of the car we're going to model as a flat plate, friction. Force on the parachute is going to be a bluff body force of drag in that particular case. Alright, well let's look at the car first. Let's calculate the force of drag. Well, the first thing we need to do is we need to look at the Reynolds number to see if we're either in the turbulent or laminar flow regime. So Reynolds number equals rho v L over mu. And we need some properties. Let's say the density, 1.201 kilograms per meter cubed, and the viscosity is 1.8205 times 10 to the negative fifth Pascal seconds. And that should be enough to perform all the needed calculations. Reynolds number, 0.201 times by 5 times by the length is going to be 3 meters. The viscosity is 1.8205 times 10 to the negative fifth. Gives a Reynolds number of 9.9 times 10 to the fifth. Going back and looking back at your notes, that is going to be greater than 5 times 10 to the fifth. Therefore, we should utilize the turbulent flow regime model to come up with the coefficient of drag of a flat plate. Coefficient of drag, 0.031 divided by Reynolds number raised to the 1/7 power. Taking that value, raising it to the 1/7 power, and putting that value and dividing that value by 0.031, or taking 0.031 and dividing by the Reynolds number to the 7th, you get a coefficient of drag of 0.0043. Alright, the force of drag on the car, therefore, is 1/2 the coefficient of drag, rho v squared A. Now, this is going to be, we're making our flat plate assumption. That should be 1.5 meters. 1.5 meters wide. So the area of the top surface is going to be 4.5, but we also have a bottom surface. We want to include that, so you have a force of drag on the top and the bottom, but we'll just combine that as a double area. So 1/2 0.0043 multiplied by 1.201 multiplied by 5 squared multiplied by 3 times 1.5 is 4.5 top, 4.5 bottom. Area is 9. Therefore, coming up with a force 0.58 newtons. If you're able to have a car that is represented as a flat plate, that's a pretty small force of drag, which is good for a racer. You don't want to have a lot of frictional forces stopping your motion. Alright, well now let's calculate the parachute. Well, first we want to calculate now the Reynolds number due to the parachute, which is going to be on the diameter, which is rho VD over mu. Diameter is 1.5, 0.201 times by 5 times by 1.5 over 1.8205 times 10 to the negative fifth. Gives us a Reynolds number of 4.9 times 10 to the fifth. Now we didn't actually have to calculate the Reynolds number because for bluff bodies we want to make the assumption that it's going to be relatively constant over a certain range. So in this case, make the assumption that the coefficient of drag stays the same over our regime of 1.2. So coefficient of drag is 1.2, therefore the force of drag due to the parachute is 1/2 coefficient of drag rho v squared a. 1.2 divided by 2. .2 is the coefficient, divide by 2. The density is 1.201. The velocity is 5 squared. But remember our area, it's going to be the frontal profile. So the frontal profile of a parachute is a circle. So the frontal profile area equals pi r squared. The radius is 0.75 squared, and you get an area of 1.767. And that should be meters squared. Therefore, you get the force of 31 newtons. Force on the parachute is much, much greater than the force of friction. So the total, force total equals the force of drag the parachute plus the force of drag car. 31 plus 0.58 gives us 31.58 newtons. But remember, we need to utilize the correct number of decimal places. So this has 0 decimal places. You want to round. So it does have that effect. You get 32 newtons. 32 newtons is the force they would report. But again, it's plus or minus 1 newton. Okay, that concludes the continuation of the calculation of drag forces.